pleasure to have you guys here. I see many familiar faces, and we have wonderful speakers, keynote speakers, invited speakers, and also excellent presenters. We're going to actually be filming that, so hopefully we're going to be able to put it on YouTube, except for my session, perhaps. Yeah, we start today with Bas van Fraassen. Bas is a distinguished professor of philosophy at San Francisco State. He came to us after being for a while in Princeton, and it's great to have him here. Bas is, of course, well known to all of you. He has a very well-known book on quantum mechanics, where he puts his interpretation, modal interpretation of quantum mechanics. But he's also one of the perhaps most important philosophers of science we have alive. So hopefully he'll continue like that for quite a while, right? So I'd like to welcome Bas for his talk, and welcome you guys as well for the conference. Thank you.
Well, thank you. Thank you for inviting me. I'm happy and honored to be here. Let's see if I can get this started. So what I would like to do is I want to go through shift interpretations in quantum mechanics over the last century, and then offer an analogy to quantum mechanics as it's understood in one sort of view, the view that I call external observation view, an analogy to use for solving problems in formal epistemology. So these are the terms I'm going to use, the external observation view, I should say kind of view, roughly associated with the Copenhagen tradition, a shift in the middle of this period, the point where everybody opted for a very different kind of view, which I'll call different kind of view, called the closed universe view, and then how in just the last few decades there was a reaction, shift back to an information theory approach, which goes to some extent back to the external observation. The reason I want to do this is because the analogy I want to build on for formal epistemology makes sense from the external observation point of view. So formal epistemology is epistemology of the sort where the state of opinion of an agent is represented by probability functions. And what I want to do is apply the sort of reasoning that you're familiar with in quantum mechanics to problems that they have. The information theory approach in quantum mechanics drew a lot of inspiration from formal epistemology, so I'd like to go and see if we can go a little bit in the opposite direction. So, there's been many interpretations of quantum mechanics by now, right? And in the 60s to 80s, I would say that the main interpretations being discussed, debated, advanced, proposed, were all versions of what I call the closed universe view. In that sort of view, the state is a physical characteristic of the system. Observation or measurement is an interaction between quantum mechanical systems inside a larger quantum mechanical system. Specifically, the cosmos, the universe as a whole, is a quantum mechanical system. Or at least it's possible to have a closed and isolated quantum mechanical system. Now, that was a shift. It was a shift away from the kind of working philosophy of the physicist, which was introduced by the Copenhagen people. But in the Soviet Union, this was always the view of quantum mechanics, because they thought of Copenhagen as idealist and positivist, not compatible with materialism, right? In the West, this shift came in the 50s, and well, there's a way to date it exactly, if you like, which is 1957. In 1957, when Everett's dissertation was published, with a commentary by John Wheeler himself said, here we have a big shift in interpretation. He says, contrary to the tradition that we all know, quantum theory describes the world independent of observation. The model has a place for observations only as interactions between physical systems, measurements in a physical sense. And the cosmos is a system in the domain of quantum mechanics. Now, what exactly was the view, the kind of view that was being replaced with the external observation view? It kept the observer always outside the system. States are described on the basis of observations, the results of measurements. And so a state is assigned to the system that's being studied and measured, not to the apparatus. Now, you can take part of the apparatus and put it into the system you're studying. Right? You can study the Geiger counter together with the radium sample, for example. But there's always a step back. There's the measurement of that, and the state of the studied system is based on the outcomes of the measurements of that system. So it really doesn't make any sense at all to talk about the state of the ultimate observing equipment, and it doesn't make sense to speak of a state of the whole that encompasses everything. Now, there were reasons why people went away from that. There was a real tension in that kind of view, because if the state is determined by the information gathered, then what sense does it make to talk about the state between measurements, or the state of a closed system? And that matters because quantum mechanics gives us very explicitly a model for the evolution over time of a closed system, the Schrödinger equation. Right? So the question is, how can we reconcile these things? And although these kinds of views were developing in various ways, there was, as I say, a real shift to, no, let's think about it the other way. So the closed universe kind of view resolved that tension because now the state, the values of the observables, they're not just a summary of, say, measurement results. No, they are physical characteristics of the system. And the measurement tries to find out what they are, and on the basis of that, predict what's going to happen next. The measurements then are there, they're important, they reveal values that are had at the end of the measurement. But the measurements themselves are just interactions between the object and apparatus in which they become entangled. The state becomes an entangled state. Now, I'm sure you all know now there's a new tension, because in fact, reconciling B and C, that's what's called the measurement problem. Right? And so these kinds of view also have a big problem. So all the different versions of all these different interpretations that were being proposed, say, in the 70s and 80s, they all had that problem, and each of them offered a solution that nobody else accepted. So at the end of several decades, it's not surprising that we see a shift again. People are trying to do something new again. So there was a reaction, and there are new approaches. They hark back to the external observation view in some respects. To some extent, they're inspired by formal epistemology because they say the state is an information state, and it's represented by in terms of probabilities, and so they try to apply the theory of subjective probability, decision theory, information summary of the observer's information. Now, that, as a suggestion, that started at what I would think of as the end of the period when the external observation rule was being developed. And I would refer specifically to Grunewald, who started this in the 1950s. Now, he's not very well known in other respects, but I think his papers were important for this. Recently, we have interpretations by Carlo Rovelli, Jeffrey Booth, Chris Fuchs, and some of them sound, quite radical in the way that they want to go away from the closed universe view. Let me begin with Grunewald, so that we get some details about how this was supposed to work. So Grunewald says, if we just look for the empirical content of quantum mechanics, what we find are an answer to the question, given the outcomes that we have registered in our measurements, what are the probabilities of the various outcomes of the next measurement? And the kind of schema that he uses in order to depict what is happening here is a very familiar one. At the macro level, a level where that we are directly in touch with, we have an apparatus that is supposed to measure the value of a certain observable. It's a bit of a black box process as far as what we can see is concerned. At the end, you get an outcome which is one of the eigenvalues of the observable. At the same time, we have a model, the quantum mechanical description, which says that the measurement was made on a system in a quantum mechanical state, psi, and in the quantum world we have an evolution of this physical setup, so that the state of the system changes, and in the von Neumann type of measurement is a projection, right? Projection of the sort at the bottom there. Now, Grunewald says, think of a series of measurements coupled in this way. The system is subjected to a series of measurements, and what happens according to quantum mechanics is the system has a state, it evolves, and it's constantly, it's a deterministic evolution that's constantly interrupted. Right? At the same time, at the surface level, each measurement apparatus records an outcome, a number of values, right? And these can be measurements of different observables, of course. Now, what we know, well, one thing that's non-classical is there's not going to be a single quantum mechanical state that you can describe that will give you all these outcomes, right? Because it will be incompatible observables being measured. So how does the physicist react to these records? Well, Grunewald says, depending on where you start in the series and where you end, you'll be assigning different states. And also depending on the information about the setup that you start with, you'll be assigning different states. So what the state represents is not what the system is like. What the state represents is the information that we have about the system. Of course, this echoes more, right? And if you start with no information, well, you can always use the identity operator just to factors of the information state. But right, what you start with makes a big difference. So he says there's a subjectivity and an objectivity in this situation. Different observers will assign different states. Right? That's the subjective part. But there's something objective. There are absolutes. And specifically, he says the transition probabilities, which quantum mechanics gives you for this kind of setup, that's absolute. That's independent of the observer. So different observers will assign different states. They'll use the same theory that gives you transition probabilities in order to make their predictions. And the evolution operators that depict how the system evolves between measurements, that too is given by the theory, and that's an absolute, there's nothing relative observer dependent about it. Well, the later people working on this say some very radical things. And I've taken Jeff Cook, who's not as radical as Chris Fuchs, by the way, but rather radical from the 80s point of view. So he's one of the people developing these information-oriented interpretations. He says the quantum theory is best understood as a theory about the possibilities and impossibilities of information transfer. You can tell a mechanical story. Now he's referring to the closed universe view kind of interpretation. You can tell a mechanical story about quantum phenomena. But if the story is already constrained by these information-theoretic principles, it doesn't add any empirical content. So the mechanical story for quantum phenomena, that's like the ether story for say for Maxwell's equations. Right? In other words, yeah, it can give that, and maybe it will help the imagination, but it doesn't really do any work. I think that the one interpretation of in this family that I want to say something more specific about, to give us a good feel of how it worked, at least briefly, is the one by Rovelli. Rovelli's relational quantum mechanics, which he proposed in 1996. It's information theory oriented to some extent. In some important respects, it goes back to the external observation view. At the same time, he tries to resolve the kind of tension that led people away from that. So in Rovelli's world, quantum mechanics as interpreted by Rovelli, the states are observer dependent, and the values of the observables are also observer dependent. And there's a quick reason for that. Just like for Neumann, we insist that an observable has a value if and only if the state is an eigenstate. So, and if the states are observer dependent, so are the values, obviously. So in that case, what about, John Wheeler's concern that we have to make sense of the idea that the universe as a whole, or at least any closed system, isolated system, could be a quantum mechanics system? And his answer is, yeah, yes, we have to do that. And when I talk about observers, what I'm doing is the same thing as Einstein did in 1905 in his special relativity theory. Okay? Because that paper was all about, people standing on station platforms, sending light signals to the conductors on trains. It was all about human observers. But when the theory is developed, it's not about human observers, right? It's about frames of reference. And he says exactly the same here. When I say observer in my discussion of quantum mechanics, really, that's a metaphor. It's that in my theory, there are information states assigned at every system for other systems. And the content, the non-vacuous content of such an information state can only get there by physical interaction. So for him, there is a quantum mechanical picture of what's happening in measurement, the quantum theory of measurement about interactions inside the closed system, that is part of his theory. And so this gives him a kind of objectivity that in the Copenhagen tradition that was not. I find his relational quantum mechanics a very interesting interpretation. In my eyes, it is not complete. The interpretation is not complete, but it is a return to the external observation view in this sense that in Rovelli's world, different observers will assign different states to the same system. Okay? If you imagine one observer who is making a measurement, on the basis of the measurement he assigns a state. Imagine another observer who is observing that process, but not yet interacting with it. Maybe he will check later, right? So he knows something about the state of the observer apparatus system. Right? He has a state for that, and he knows how it will evolve according to him. He will make predictions on that basis. He's assigning a different state to the system. By reduction of the density matrix, he gets a mixture, whereas the first observer assigns a pure state. think that whether you are already familiar with Ravelli's theory or not, I'm sure you're already thinking about puzzles and questions of consistency about this. How can that be consistent? So I don't have time to talk about that if I want to do the second part of the paper. But I wrote a paper about it. It's in Foundations of Physics. It's also available on my website. Of course, I can try to answer questions about it if you want to talk about Ravelli, who's a very interesting writer. Okay, so I've tried to say why I think that the external observation U in one form or another is something is something we should take seriously, which a couple of decades ago people didn't do. And that the analogy that I want to develop will be to this constantly interrupted deterministic process that you see in that kind of view as a model for what happens in quantum mechanical world. With the states being information states, well, in formal epistemology, we are talking about agents with states of opinion, information states, if you like, represented in the same way in probability theory and information theory. So, I'll quickly sketch the analogy, then I'll say what are the problems in formal epistemology that to some extent have been solved and to some extent not, and then suggest how with this quantum mechanical analogy we get a hold on how to solve problems of that sort. So, the target of the analogy is an agent, a person's state of opinion over time, but as represented by probability functions, subjective probability. And the basis for the analogy is how the quantum state develops over time in that kind of external observation view. I want to make it part of the basis that the usual mathematical representation applies. States are elements of a vector space, and this process, the deterministic process that happens when it's not being interrupted, right, is a transformation of the vector space by a dynamic group, a group of unitary operators that characterize that system. So that will be the basis of the analogy. Well, what are the problems? In epistemology, we're dealing with knowledge, belief, and opinion. In formal epistemology, it's basically opinion that we deal with, represented by subjective probability functions. And a person has probabilities for what is going to happen, then he gets some new input. We call it experience, typically called experience, but it could be reading a technical paper, for example. Gets new input and says, oh, my opinion has to change, because this new input has to be accommodated. So the new input, whether it is from perception or reading or whatever, it puts a constraint on what your opinion should become. So you have a prior opinion, and you want to form posterior opinion subject to that constraint. And every input can be put in that form. The function of the input is to put a constraint on your posterior opinion. But then the constraint, of course, is going to leave a lot of things open. And the question is, which posterior opinion that satisfies the constraint is the one I should go for? That's the form of the problem of this subject. Now, some results are well established. So there's simple conditionalization, sometimes people call it Bayesian conditionalization, when the constraint is, here's a proposition, become certain of it. Somebody comes running in from the garden and says, I just saw a flying saucer. Okay. Well, he has accepted the constraint that to be certain of the existence of a flying saucer, and he has to adjust his opinion to that. Right? And well, the rule is very simple. If your probability mass is sort of distributed over the possibilities, you wipe off whatever is, outside that proposition. And the rule is the conditionalizing the probability function. Now, that's established in the sense that there is a theorem. It's a theorem by a symmetry argument. And the theorem is that if your posterior probability must be a function, and I mean literally a function, of the prior and this new proposition, then there's only one equation that will do the job. Okay? By a symmetry argument, you establish that's the only equation. And that's the Hartlov-Bayes theorem. A second development of this sort was Richard Jeffrey proposed that sometimes you can become certain, but you suddenly realize that you need a new probability. I guess the easiest example would be, I think it's not going to rain today, and then in the morning I hear the weather forecast, 80% chance of rain. Okay, change it to 80%. Don't become certain of this proposition, but change it to probability 80%. And his rule, also quite straightforward, he says, well, divide the possibilities, the ones in which it will rain, the ones that won't rain, give the new probability to this part, and 1 minus the new probability to that part, conditionalizing in this case. Now again, there's a theorem, a very similar theorem, a very similar symmetry argument, though a bit more complicated, right? That says, oh, if the posterior is supposed to be literally a function of your prior and their constraint, that's the only thing to do. All right. But then, again in the 50s, those famous 50s, people started talking about other constraints. So, what if I only hear part of the weather forecast, and the forecaster says, the probability of rain and snow for today will be equal. And then he says, namely, and sorry, I didn't hear the rest, okay? Now what do I do? Right? Or suppose that he gives new odds. He says the odds of rain and snow are 73. He doesn't tell me what the probabilities are, he just tells me the odds, okay? Or he says, change your conditional probability. The conditional probability of rain given snow is 0.8. Okay. How do you solve those problems? Well, a physicist, Richard James, proposed that we look at a very general form that really covers all the ones I just mentioned. You've got a quantity with an expectation value, and the input is, oh no, the expectation value is such and such. So the definition of expectation value, it's, you take the values of the quantity for the different possibilities and you weigh them with their probabilities. And that sum is called the expectation value. And when the forecaster tells you the expected precipitation over the next week, it's giving you an expectation value. Okay? So James didn't have a theorem. James did have a suggestion. And it was using information theory. And what he proposed is, he called it maximizing the relative entropy. Well, the way he conceived of that, it was equivalent to minimizing the relative information. So the intuition is, you've got your prior opinion, you want to form your posterior opinion, and you want to stay as close as you can to the prior while satisfying the constraint. The question is, what does close mean? And he measures closeness by the amount of relative information in the posterior given the prior. And the information theory formula probably looks familiar to a number of you. It's noticed that this is an expectation value. Expectation value from the posterior point of view is the posterior expectation value of a quantity whose values are the log of the ratio posterior to prior, right? Now, that is a log actually just has to do with mathematical niceness, that you want to get a nice formula there with mathematical properties. So the crucial factor that is supposed to be measuring, and that seems reasonable, the distance of the posterior from the prior is this ratio between the probabilities. So okay, I think we can honor that, but still, I'd like to say, wouldn't it be nice to have, just like for the other results, a symmetry argument and a theorem that says that's the right answer. So that's what I want to suggest the quantum mechanical analogy for. Let's think just about a finite case to keep it quite simple. In that case, you have a finite set of possibilities. You keep them ordered. Each possibility is assigned a probability. And for any quantity you have, each possibility has a value for that quantity. Like 1 inch of rain, 2 inches of rain, etc. Right? So you see that the probability, so these are vectors, right? You can see that the probability is then just a special case of a quantity. The statistician doesn't say quantity, the statistician says random variable, but it means the same thing. Okay? And the expectation value is just the inner product, the dot product of the two vectors. So now you see how we can apply the usual formalism that we use in quantum mechanics. The other thing we should say immediately is that a probability function, probability is a quantity whose values add up to 1. But, and that's the only special feature there is, they're positive, I'll stick to positive numbers. Positive numbers adding up to 1. But that they add up to 1 is just a convention. That's not important. The information that you get comes from the ratios, which are the odds, right? So in a horse race, for example, you never see the probabilities posted, you see the odds posted. That's enough. That's all the information there really is. So a probability factor like 0.5, 0.3, 0.2, well, an odds factor, 5, 3, 2, 10, 6, 4, will give you the same information, as long as you know it's the odds. And why am I doing this? Because if we work with the set of odds factors, which is a somewhat bigger region in the space, it'll be easier to handle mathematically. And so if we agree that those ratios measure the distance, then let's say here we have another vector, which is the quotient of two vectors, which is just, it has as elements the ratios, okay, for that quotient. Now what we're looking at is we're looking at this vector space, a certain region, a small region has the probability factors, a larger region that is the positive odds factors, right? And what's the significant structure in that region? Well, first of all, the quotient, that's supposed to be important. And secondly, linearity, because if you have a linear combination of odds factors, you've got another odd factor. Okay. So a symmetry will be a transformation that preserves just that. It preserves the quotients, those ratios, and it preserves the linearity, linear combinations. Okay, now I think you see the analogy to unitary operators, right? And because this is such a simple, much simpler case, real vector space, let's say that, let's use the term uniform, right? U is a uniform transformation if it's a symmetry. It preserves the quotients and preserves the linear combinations, okay? And quick theorem, in that case, U just multiplies the elements by certain constants, or to put it another way, you can represent it by a diagonal matrix. Yeah, no, that's to be expected, I guess, with this analogy, right? But that's important because that means that we can now think of it as the kind of transformation that will work no matter what your prior is to give you the right answer under the right circumstances. So, all right, then, now we have to go to the evolution over time. And so in quantum mechanics, we say, well, the way the closed system evolves over time, it's subject to a dynamic group of one parameter group, the parameter being time, right? That changes the state over time by the application of that group. Well, here's the analogy then. A uniform motion will be similarly a one parameter group of uniform transformations, the parameter being time. And again, it's a fairly big theorem that says, oh yeah, okay, each of those operators in the group will be represented by a diagonal matrix of which the elements are E to a power which is a constant times time. Now, that's not far enough because these uniform motions, they could still take you far, far away from the prior, right? What we want to say is subject to a constraint that has to stay close. So we have to introduce this intuition of being conservative, staying close. Well, we've got already something that looks, that you see everywhere in physics, biology, economics, this exponential grow over time, right? And so the simplest example is a person who is making investments. So here's my goal. By age 65, I want to have $1 million so I can retire. Right? But I have a constraint, which is I worry about emergencies, so I want my investments to be liquid. Liquidity means ease of getting it out when you need it. Right? So how do I, now you've got an optimality problem, how do I reach my goal by age 65 while maximizing liquidity? And the bank knows it's important, so they say higher liquidity, lower interest rates. Right? So it's the same as saying, well, while minimizing the interest rates, unfortunately. Okay. I'm going to introduce then this optimality postulate that the transformation has to be such that you can say that it, what should I say? It satisfies the constraint you put on while minimizing the move away from your prior. So here is the postulate. The transformation of the prior rods to the posterior rods, subject to a certain constraint, very general, is by a uniform motion. And remember that the elements, the components, they are all the form E, K sub I, Z, where Z is the time, right? So K sub I, K1, K2, K3, these are values, numbers. So they're values of a quantity. Quantity that has certain values in these different possibilities. Well, here's my constraint. The posterior expectation value of that quantity should be as low as possible. That's like, saying I'm minimizing the interest rates. And then we have a theorem. Suppose that you say my posterior has to be a probability function. That's number one. Secondly, as change required, I have a new input, which is a new expectation value for a given quantity Q. Well, in that case, there exists a single number, a constant W, such that the transformation of the prior to the posterior is by a uniform motion in which the components of the matrix are very simple. It's just E, every component is raised to the power the same constant W, the value of the quantity, and the time. Okay, well, at the moment, and I did this fairly fast, it looks pretty abstract, right?
Fourier transform?
It's not a Fourier transform, but it's, yeah, it has the same sort of form. Yeah, right. But, so, okay, that's one thing to say about it, and that already for a mathematician brings it a bit more familiar, right? But here's what I see as the meaning of the theorem. Because, as a matter of fact, it gives exactly the same answers in applications as James's maximum entropy formalism. So that's what I wanted. I wanted the theorem, where James had only a suggestion, a theorem by a symmetry argument, symmetry plus optimality, which tells you that's the right equation. And of course, by reasoning, that was analogous. I was just saying, let's use this analogy. Right? Apply the analogy and say, this is a deterministic process, interrupted by the inputs. Right? Okay. So that's what I wanted to tell you. I want to tell you, yes, using this analogy, I get to a theorem using symmetry and optimality to establish that this is the right answer. No, but now something important here. This is the right answer in the sense that these symmetry theorems give you the right answer. And remember what I emphasized. I said the symmetry theorem begins with an assumption that the posterior is a function. Now, what is a function? It's a single-valued relation. It's a function of the prior and the constraint. And so, what I would add to this is that it reveals an assumption of determinism behind the idea of the maximum entry for formalism. And actually, I would add to this that it's an assumption, this kind of assumption of a deterministic process in the way that we rationally manage our opinion is an assumption that is behind much of formal epistemology. And so, if I ask myself, was this a good result? I have to say, no. Well, you see, I think in epistemology perhaps we should have more respect for free choice. But anyway, so far, this is the result. Okay, thank you.
Oh, that integral, the exponential that you had,
Yeah.
reminds me very much of the Lagrangian, the principle of least time, the action principle. Max sounds, is that similar to the standard?
Yeah, well, first of all, in applications, I use the Lagrangian multipliers, and in proving the theorem, I use the Lagrangian multipliers, you know, which is typical for optimality.
But is it different than the standard version of principle of least action, that Feynman did Wheeler?
No, it's not really different. I mean, formally speaking, I would say it's not different. You see, it's the same kind of formalism, the same kind of reasoning, right? It's just that I could only see this reasoning coming by exploiting an analogy, right?
So glad you finished with determinism, because before that this question would have sounded rather quirky, but it's something of a historical question. Let's say, just for the sake of argument, that 300 years ago they already had quantum mechanics. So you've got philosophers and scientists like George Berkeley and Descartes and Leibniz, and who would have had no problem saying, oh, we need an external observer, God, fine, done.
Yeah.
Scientists agree.
Yeah.
So all of those problems wouldn't really be there, but the determinism problem, well, hang on, if there's this external observer who we all agree is God and everything's fine there, but we still can't predict which slot the electron's going to go through.
Right.
How do you think they might have approached that problem?
I mean, different from, say, Rovelli, right? This is a really delicate and subtle problem here. I mean, let me put it in the context of Rovelli, where, you know, you can, the observers are inside the cosmos, and Rovelli himself is a human being, he's an observer. He can assign a state to the rest of the world, but not to the world as a whole, okay, in his theory, right? So, how can he say that we've, you know, gotten away from the problems of the external observation view? Well, Rovelli, the theoretician, describes the world as a whole. Okay? I mean, in that sense, he's playing the role of this God. At the same time, he has to admit that as an observer himself, he could never have the knowledge of what that state really, well, he couldn't, it doesn't make sense for him to assign a state to it. But when he describes the world as a whole, he can nevertheless say, oh, but you know, this as a whole, it has an evolution governed by the Schrödinger equation. I just don't know the details. And I have partial details. I never have more than partial details. Right? In the 17th century, would that have made sense? You see, it's different because there we don't have to say that, well, God is just giving a theoretical picture. According to them, God had all the details. Right? And so, maybe the problem, if they are totally immersed in that assumption, they don't have the problem. Right? They don't have the problem. Rovelli really struggles with this. I mean, Rovelli's world is an indeterministic world. Now, maybe I should have emphasized this, that most of the closed universe views made the world deterministic. Everett is a very good example. The world as a whole is deterministic. We all have little partial bits of knowledge, right? Rovelli's view, that's not true, because the outcomes that are actually registered in the sense of added to the information state at each system, independent of the absolutes in this theory, which are the transition probabilities. So it's an interesting medley or combination or compromise between real indeterminism and a deterministic model. I don't know how the 70s century would be a bit right.
So I think to interpret what you say, so they might have effectively put the indeterminism we see down to human frailty and and then
I think so. Just partial knowledge while thinking there is a complete knowledge that exists. Okay, two questions.
Okay. Yeah, the Ravelli is very interesting to me. I'm a major follower of the interpretations of quantum mechanics on the Wikipedia site, where unambiguously Ravelli is playing for the wave function to be not real. So that does put him up with the idealists.
Yeah.
But is that because it's information? Because in all other respects he's so close to von Neumann, where it's real. So how is information? What is the reality?
Okay, so there was an article in the last foundation of physics by Henry Spearn, who criticizes Ravelli on this point. He says, Ravelli says, the measurement is real, the outcomes are real, but then he says about measurement that it's just an interaction establishing a correlation between systems. And that correlation does not, of course, give you a unique outcome. Well, what Spearn is not doing is not taking seriously that in Ravelli's relational quantum mechanics, the registered results are actual. And in fact, that is an objective part. That, like that in a particular system, you have a series of eigenvalues that we think of as results of measurements. Now he says you can only get it by physical interaction. But you see, that's the indeterminism in his picture.
But the wave function is unambiguously not, or is the word real, do we have to define what the word real means? I think that's where most problems come in, is that different people maybe mean different things by that one word.
Yeah. Well, I don't want to use the word, I shouldn't use the word real. I want to say there are absolutes in this theory, and there are things that are relative in this theory. The information states are relative, always relative to, for one, the information state of system X is the one that is assigned at system O, okay? And from system P, X will have a different state, right? That's relative. The algebra of observables that characterizes a system, the transition probabilities, the evolution operators, that's all absolutes in his theory. And maybe that's the best I can do at the moment. Yes?
Yeah, I just would like to ask you to say something more about this conservatism. Like, is that a normative constraint that's being introduced here, or why should it be conservative?
Yeah, that's. Yeah, why should it be conservative? Yeah. Now, by insisting that it is conservative as measured by a specific standard, you're actually saying it's a deterministic process. And I wanted to explore this. I wanted to see what theorem was possible. But in epistemology, I have a more libertarian view. That rationality does not require that you never stray from a deterministic recipe. But that's outside this, obviously, because here we have a theorem that gives you a unique answer when the question is asked.
We can't argue with Einstein that you don't need something like consciousness for special relativity, but I don't see how that applies to the measurement problem. Vigneault's friend notwithstanding, I mean, if a machine entangles with a quantum system, that doesn't necessarily mean that the results are going to collapse.
Right.
So my question is, what's your opinion of the Penrose objective reduction approach, which actually gives you self-collapse and consciousness?
You know, I don't know Penrose's work well enough to answer that part. But I can answer the first part of your question, which is, I think I mentioned that I think Ravelli's relational quantum mechanics is incomplete as an interpretation. The actual registered values are values of observables being measured, right? But in his theory, they are observer dependent because the states are observer dependent. And the states and the values go hand in hand with this eigenstate, eigenvalue link.
But what's the observer?
Any system. Okay.
So machine would be an observer.
Yeah, oh yeah.
But that wouldn't necessarily cause a collapse. The results could stay in superposition in the machine.
Well, you know, in Ravelli's world, the states are collapsing, but they are just information states. But what should I say? The world is not collapsing. There's no physical collapse of anything. Okay.
And there's no wave function either.
Yeah, there's a wave function, which
It's not real.
Well, a wave function is a mathematical object. In that sense, it's real. But what it represents, according to him, is an information state. It doesn't represent the physical characteristic of the system. Okay. Now, okay, you know, I know I'm feeling a bit ambiguous because, as I said, I think his interpretation is not quite complete, right? I had suggestions for him. And so we had a symposium in Avignon, and I suggested that he needed to draw on the modal interpretation for some ideas, and I made specific suggestions about it. And his reaction was, that's not empiricist enough. But no, I think that what he ought to say is, look, the state and the value of the observable, that's something that has to come apart, really. And the actual values registered, right, are something that's independent of the deterministic process that underlies any evolution of the state in between measurements. But so that's going to be a big story. Right? Yeah.
I have a question about when you, it's more general on
Yeah.
philosophy, quantum, and physics also. When you talk about prior and posterior,
Yes.
and there's the notion of time.
Yes.
And so in some way this is a constraint. When you think that things are ordered in time, then you say that things come before, and then of course then we have this function, constraint function. But my question is, could this constraint function be independent of time, meaning it's sort of a symmetry problem, and not depending on this prior or posterior? So something which is, I'm a physicist, so I know in physics you have some invariants which are more or less the relations, things come up through theory. And this is something which is above this time interpretation.
Yeah.
So it could be some structure which is whatever, and you don't need to talk about information or whatever. It's sort of how the world is made.
Yeah. Yeah.
Could this be something
I have to say,
that
I
guides
don't know.
this kind of?
I don't know. I was staying with, and Ravelli does too, staying with the quite elementary quantum mechanics, which in its time is the independent variable, right? So we were just working on that. So, I mean, I think it's very interesting to suggest.
Because when you do physics, sometimes you have this problem because are things depending on time, or are things just, you take a crystal, you have all this, everything is there.
Yeah.
So you don't need to think about time, or
Yeah.
you have this structure which is least action principle gives you this, builds the structure. For example, crystal is built, and you have all the symmetries inside, meaning that this is sort of an invariance. And,
Yeah,
and
when
then time comes up when you do the measurement.
Right.
It's a large.
Yeah, it's an interesting idea. At the moment, I don't know more to say about that. Yes.
Perhaps it's a bit technical question, but how far does your theorem generalize beyond the random variable plus finite number of
Oh
variables?
yeah. Okay. Well, it's there's several limitations. I mean, one. I mean, now we're talking about mathematics, so to what extent we can do better than just a very simple case, right? And the first problem that has to solved is what do you do with zeros? So if you think about the definition of relative information, for example, you can't divide by zero, so there can't be a zero in the prior. But secondly, the log of zero isn't defined, so there can't be a zero in the posterior either. So what do you do, right? Now, there's different ways of starting with that. I mean, you could use the extended real number system. That's probably the most straightforward way to deal with it. Then generalizing to what innumerably many, or in fact, say, instead of using sums, use integration. And information theory is developed for the case of uncountably many possibilities, where you use an integral instead of a summation. So in principle, I don't think there's going to be obstacles to generalizing. If the analogy with the unitary operators holds, then again, that shouldn't be a problem. And uniform motion is just, I think, the simple version of unitary operators.
The notion of relative information itself is best defined for a finite number of
Yes,
functions, with non-zero probability.
Right.
And then as you go even to simple continuum and use integration, well, there are already some variants there.
Yes.
You know, but I do not know how to do it beyond that,
Mm-hmm.
except for some kind of discretization.
No, you know, I'm not a mathematician. I consume mathematics, you know, rather than create it. And so looking at how they've dealt with this, Tribus and others who developed the maximum entropy formalism, it looks to me like it is all possible, but I'll leave it there.
You might be able to use compactness.
Yeah, I think you have to start putting some constraints on it, like, you know, the constraint regions shouldn't it be convex and maybe compact in order to, yes, yeah. Maybe I can add a little advertisement here. I think that using this kind of formalism in formal epistemology can be useful in many other ways. And Joe Halpern and I wrote a paper that's just in the British Journal for Philosophy of Science, in which we use convexity results in order to get some answers there.
A bit more general question. Now, I'm afraid I may not be very clear in asking this question, but is there any problem in when you consider, you know, different interpretations of quantum mechanics? We talk about system, random variables, measurements. Is there a problem of identification of random variables as a fundamental problem? Which random variable we are dealing with? For example, I'm measuring it now and I get an outcome. I'm measuring it later or in another context and getting another outcome. How do we know that these are outcomes of one and the same random variable rather than two different random variables?
Yeah. That's a question that has bothered me quite a lot. I mean, I would say physical quantity or observable instead of random variable, but the question is there. And I would argue that the answer is often theory dependent. That if you take your stand in one theory, you will answer in one way. It's not going to be a theory independent objective or empirical question in many cases. Akaccio, we're watching the time here.
We have a very long coffee break.
Oh, okay.
Perhaps we could reduce the coffee break and then resume in about 15
Or-
Mhm. Okay, well, so what I was proposing is perhaps instead of like following the program, I don't know who wrote that program, we could take a shorter coffee break and start at 10:30 instead of 10:45. Then we could have lunch earlier. I'm already hungry. And we have some coffee outside and other things.